waiting here.
Yeah. Hi, everyone. I'm really happy today to have Ali Tajer from RPI, and he's going to give a talk about active sensing for quickest detection in networks.
All right. Hi, Salim, and everybody. Thank you very much. So let me start sharing the slides, right? So do you have the slides now?
Yeah, but maybe if you can make it full screen. Yeah.
All right. So I've lost your videos, but I guess that's fine, right? I don't have to see you.
Yeah, I think you'll hear us.
Okay, all right. Okay, I'll have your voice. All right, thanks. So I'll just quickly go over a couple of things. The common theme in what I'm going to talk is looking at networks which undergo potentially anomalous behavior. And when the anomalous behavior happens, we want to detect them with minimal delay after the anomaly has happened. Okay, so this relates to a couple of notions, specifically quickest detection theory and the notions of active sensing in networks. And that's motivated mainly from the perspective that in networks, generally, we could have significant amount of data. But when an anomalous happens, not every segment of the data is informative or equally informative. So we want to see if we can come up with procedures, algorithms that could very quickly focus on the segments of the network that are most likely the parts that have undergone a change or anomalous behavior. And we could sense and collect data from those localities. Okay, so that is the common theme of the presentation. So to motivate it, let's start with a very simple example. So consider the standard 39 bus power grid model. Let's assume that some anomaly, like a line outage, happens somewhere in the network. So if that line is cut, its power will be distributed over its local or neighbor buses, right? So you'll see that when in such a network an anomaly happens, the effect of the anomaly does not happen in that exact location. It'll start propagating throughout the network to different degrees based on the application or the significance or severity of the anomaly. In a different application or motivating example, you could think of a surveillance system. You could imagine a grid of cameras. On the left-hand side, when there is no object, they're just collecting data without being induced by any object, which could be essentially background noise. And then at some point, there could an object appear in the system, and then the cameras around that object, which is, let's assume, in the middle of that red grid, then neighboring cameras will start sensing it. And that becomes a distinguishing factor between when we don't have an object in the network, we have purely background noise, versus when we have an object. So in both, again, in this example, we'll see that the effect of the change, the appearance of the object, could be represented by a change of the covariance of the data that we have or we can collect from the network, right? So in both examples, the common theme is that we have some sort of network level change in the behavior of the data. It's not a single node, okay? So in a broader sense, when we talk about anomaly, it could be interpreted in a couple of different ways. The classical notion of anomaly in statistics or mathematical statistics is that these are parts of the data that somehow we want to get rid of. These are bad or non-informative data points that essentially we want to look at the data, clean it up from those outliers, right? Now, in this talk, I'm looking at the flip side of that notion, which is these anomalous data, even though they could happen very rarely, but still they represent or signify significant events. For instance, let's look at the outage detection problem, again, in power systems. We have a gigantic system consisting of many thousands of buses, measurement units, and different electrical components. And when there is a failure, we cannot just ignore it as an anomaly that we want to get rid of, but rather it's a failure that we want to be able to detect very quickly and localize also very quickly. In other domains, you could think of a spectrum sensing. So the spectrum, wireless spectrum is heavily populated. When we allow for opportunistic spectrum access, generally what we like to do is to identify the parts of the spectrum that are being unused, which now become the anomalous ones, as opposed to the significant majority that is being used, in order to get access to it and use it for communications. You could think of query search over the web, that the keyword that you're looking at compared relatively to the entire keywords that you could have on the web is a very, very significantly small portion, right? But on the other hand, it's very significant for us as the person who is searching the keyword. So in all these algorithms or applications, we are interested in devising algorithms that are fast for the objective that we have. And we can also prove certain, at least correctness or optimality guarantees for them, all right? So to proceed, let's formulate a problem. Let's assume that we have a network of interconnected entities, agents. Each of them is generating data over time. So you could think of as a real-time monitoring of the network. Let's denote the sequence of the data that the nodes are generating by calligraphic X, X1 up to Xn, representing the n nodes. And then to encode their interactions or dependencies, we superimpose a probabilistic graphical model. So the edges essentially represent the conditional dependencies that the data generated by these nodes have. Okay. Now, in the simplest scenario, when we are looking at detecting an anomaly, we could think of a nominal network that or model that we have for the network, let's say H0 on the left-hand side, that is based on the historic behavior that we know for the network. And then an anomalous behavior, an alternative to that, we could denote it by H1. Now, of course, there is no reason to imagine only one possible candidate for the anomalous behavior, but for the sake of simplicity in the analysis and describing the algorithm, let's say that in this talk, we have only two possibilities. The nominal H0, the alternative, which is the abnormal H1. And then based on all the available data that we have in the networks, so we have n nodes, n could be very large, and each node is generating a time series, we want to see that how can we determine that the network is in the healthy mode H0 or the anomalous one H1 with the minimal number of measurements that we could collect from the network. Okay, so why are we interested in minimal measurements? Because that means that we could make a decision in a quicker fashion. So the formulation becomes as follows, that given all the random variables that we have, let's say that for simplicity, again, we have one random variable per node, x1 up to xn. Is there a way to sequentially sample them to a smaller vector that we call y1 up to y tau, based on which we can discern what the underlying model of these random variables is? So this has two components, which I'll go over separately. One is the notion of sequential detection, and the other one is the sequential design of experiments. So in other contexts, you could encounter the same concept under the names active sensing or controlled sensing. All of them refer to the same thing. All right, sequential detection. So let's establish what sequential detection is first. Consider a simple hypothesis testing. Under hypotheses H0 and H1, we have two different models for the data. In a non-sequential way for this hypothesis testing, generally what we do is that we set a target for the decision reliability. Let's say that type 1, type 2 errors, we want to control them below a certain level, let's say 1% error. And then based on that, we can generally formulate how many samples we need to take. The number of samples is decided upon a priori before running an experiment. And we start collecting the data. When we collect the data, at the end of it, we make a decision. So the sample size is prefixed and specified before running the experiments. In the sequential approaches, on the other hand, we don't fix the samples that we need a priori. Essentially, what we do is that we start collecting data. After one observation, we can decide whether that data point is a strong evidence to make a decision or it's not a strong evidence. If it is not, we continue taking one more sample up to a certain point that now we believe that we have collected enough evidence to make a decision. And that is called the sequential way of detection. All right. So generally, these approaches for any even simple problem are expected to perform an order of magnitude faster. Now, the way that these two problems are formulated are in the following forms. In the non-sequential, we generally, let's say that we have a binary hypothesis. We want to control one of the error rates, let's say false alarm, and then we try to optimize the other probability. So let's say that false alarm being less than alpha, and then we want to minimize the misdetection probability. The nature of the problem in sequential approaches is rather significantly different. So in those approaches, we want to control both error types, type 1, type 2, and then we want to minimize the number of samples that we need in a probabilistic sense, primarily the average value, in order to form a decision. So the objective becomes minimizing the delay over all possible stopping times of the process and decision rules that we can design, subject that we can ensure that the decision will satisfy the reliability guarantees. And generally, this is how it works for simple hypothesis testing. We have algorithms known as sequential probability test, sequential probability ratio test. And it works as follows, that we start collecting data. And we, based on the data, we update a likelihood ratio term. So as we collect one more data, that likelihood ratio term is updated. And as long as that ratio is within specific bands, we continue collecting data. And then we will stop the sampling process. That is the point that we are confident that we can make a decision. And based on that, depending whether we are exceeding from the upper threshold or the lower threshold, we will decide in favor of one of the two hypotheses. Okay, so that is generally the structure of test for sequential testing. Now, when we look at the performance of these tests, we generally have two important measures. Now, if you remember, I mentioned that generally we want to minimize the average number of samples that we take, right? Now, depending on whether the true hypothesis is H0 or H1, the average number of samples of these processes will be inversely proportionate to two information measures, specifically I0 and I1. And I0 is the divergence between F0 and F1, and I1 is divergence between from F1 to F0. So you'll see that ideally, the performance, the delay of the process will be smaller when the two distributions are more distinguishable, which means that I0 and I1 are larger information measure values. Okay. Now, how does the design of experiment comes to the picture? In this example that I mentioned, an implicit assumption was that already we had decided about an experiment, how to collect the data. And based on that experiment, we had two distributions. Let's say that, for instance, you're monitoring a biologic organ, and depending on your microscope, if they have two different measurement noise errors, you could have different probability distributions for your data, right? And now let's assume that for running an experiment or making a hypothesis, you have two alternatives, two microscopes for observing your material. So depending on which microscope you use, you will have different distributions, F0 and F1, and based on that, you will have different information measures, I0 and I1. So selecting that experiment is becoming very important. And always the question that we face is that if I have these two microscopes, which one should I pick for running my experiment? So let's say that we have two possible experiments, experiment 1, experiment 2. Under E1, experiment E1, we have two different probability distributions, F0 and F1. And under experiment 2, likewise, F0 and F1 of E2. These are potentially distinct from F0, F1 in the first experiment. And corresponding to those, we have information measures I0 and I1. Okay. Now, how does the cycle of selecting the experiments and collecting the data and making measurements work? This is a very simple, but perhaps
Ali,
capturing
I have
all
a
the.
question.
Yes.
In the previous slide, why is it asymmetric, the number of samples required for H0 versus H1?
So in this slide, right?
Yes.
So that is due to the fact that we are running. So it is not the actual average number of samples. It is average number of samples if the underlying model is H0. And if we have a different underlying model, it should be H1. And overall, the average number of samples will be the weighted average of these two terms, right? So multiply the first term by probability of H0, multiply the second term by the probability of H1, and sum them up. That gives you the average number of samples. So the average number of samples will be one fixed number. But if you look at the two different hypotheses, they will be different, right?
So
because the data model is different.
So I was thinking, if you are under a particular data model and you know that it's not H0, then you know that it's H1. So I was expecting similar.
Yes, but in detection problems, we don't know that for sure, right? We can make a decision. We could be very confident that our detection decision is accurate 99%, but still there's a chance that it's not accurate. So we said, look, let's assume that the true model is H0 and we know it for certainty, then this will become the average number of samples, right?
Yes, thank you.
So these are two expected values under two different probability measures.
Yeah.
All right, so this is how the sensing algorithm works. So we start, let's say at time 1, we collect one sample, call it Y1. So once we have one sample, based on that, we have to select what experiment we want to run at time 2. And let's say that you're facing two possible experiments. So experiment 1 gives us information measures I0, I1. Experiment 2 gives us information measures I0 and I1 under E2. And based on that, we have to select one of the two and run the experiment and then continue the cycle. Okay, this is how the cycle is completed. Now, in this example, if information measures under E1, both of them dominate the information measures under E2, then the choice is trivial, right? Again, remember that we're always interested in experiments under which the information measures are maximized. So if experiment 1 under both is giving us higher measures, we always continue running experiment 1. So that is a trivial case. But then the more realistic case is that what happens if under the two experiments, we don't have that uniform dominance of the measures. So let's say under E1, I0 is larger, under E2, I1 is larger. Then based on how much confidence we have about the underlying model at any point, we have to dynamically select one of these two experiments to continue, okay? Now, this is a problem that, of course, has a strong precedence in the statistics literature. In a pioneering work by Chernoff, there was the notion of sequential design of experiments introduced in 1959. And this is how it works. So Chernoff proposes a very simple algorithm, which is a very strong algorithm and is optimal in many, many settings. This is how it works. So based on the data collected up to every point, it forms a maximum likelihood decision about the more likely hypothesis. So at time t, given the data collected up to time t, which are y1 up to yt, we look at the posterior probability of hi, and whichever is maximizing that probability, we denote it by hypothesis j, and that is the maximum likelihood decision up to time t about the underlying model, okay? Now, let's say that this j equals to 1. So if hypothesis 1 is the more likely one up to time t, then we run the experiment E1 if I1 of E1 is larger than I1 of E2. So essentially, we'll pick the experiment under which I1 is a larger value, okay? And likewise, we run E2 under which if the information measure I1 is larger under E2. So always the maximum likelihood decision guides us which information measure we have to look at. So if j is equal to 1, we look at information measure I1, and then for selecting the experiment, we look at which experiment is giving us the higher information measure under E1. All right, so that is how it works. And it is very simple because dynamically you can just compare these two information measures. So computationally, it's very simple. But more importantly, it admits asymptotic optimality under many conditions. Generally, when we have independence of actions, which are selections of the experiments over time, distinguishability, etc., certain assumptions. Now, so I've had now the overview of sequential detection and selection of experiments, or sequential design of experiments. Now let's see how these two merge together in detecting anomalous events over networks. Okay. So again, remember the problem is that we want to have a quickest detection of the structure of the network, under which we have a potentially very long vector x1 up to xn. We want to downsample it somehow, select only a subset of these samples via control sensing, and then have a smaller vector, and based on that, make a decision about the underlying model. The formulation is minimizing the average number of samples required while controlling the error rates, and the minimization of the sample averages over all the stopping times, all the decision rules, and all the actions, which are the sampling decisions over time. So this process could be uniquely characterized by answering the following three questions. So what is the optimal stopping time? When are we confident to make a decision? Second question is that what is the sequence of the random variables or the nodes in the graph that we should be sampling over time? And when we stop, how should we make a terminal decision? How should we decide in favor of the two hypotheses? Okay.
Ali, I have a question.
Yes.
So here, when you sample, are you allowed to sample functions of the random variables, or you just sample random variables like just the realization?
Good question. So we're sampling only the raw data, just the data from the nodes, right? But yeah, functional sampling could be very interesting too. That could give us, for instance, compressed sampling.
Yeah, exactly. Yeah.
Right. All right. So what I want to mainly focus on is to show that the second question, that is how to design the sampling process over time, is actually a problem of active design of experiments. But before getting to that, let me just give you a glimpse of how we generally answer questions 1 and 3. So let's consider this very simple problem. We have a network. The majority of the nodes, which are blue, they're generating data according to a distribution F0, and a small number of them are generated according to F1, which are denoted by the red node, and we call those the anomalous node. And we are looking into for one or fraction or even all of the nodes that are being anomalous. Okay, so this is a very specific model in which the distributions are only different in their marginals. So the sequential search for these anomalous events follow the following structure: that at some point in time, let's say time t1, we select one of the nodes or the nodes of the graph, let's say x1, and we take a sample from it. Depending on that, we decide what to sample next in the process. We could decide that the sample that we have is not informative at all, but the sequence that we have been observing is a good candidate. We continue observing that. That's an observation action. Or we could decide that this sequence that we are observing, we are not confident. We are confident that it's not anomalous, so we depart it and start exploring somewhere else in the network. Or we could be encountering a point in time in which we have sufficient confidence that we can declare exactly where the anomalous points are, and we're going to stop and we form a detection decision. Okay, so these are the three decisions that we encounter at every time. Generally, when we formulate this problem, is the way that we formulate them is that we want to control the quality of the process and we want to optimize the delay, right? These problems, we can show that they could be the two cost functions, the delay and control, could be integrated into unified cost function, essentially give us a Bayesian model for the problem, under which we are trying to minimize the probability of misdetection. That is probability of X at the stopping time not being anomalous. That's a false decision, plus a constant times the average delay of the process. Now, at every time, this cost function, depending on our action, could take different values. So corresponding to the observation action, we define cost C1. Corresponding to the exploration action, we define cost C2. and corresponding to the detection action, we define cost C3, which is essentially the evaluation of this Bayesian integrated cost under each of these three possible actions. And
I have a question. So about the model.
yes. Yes.
So here, first, do you assume these random variables are independent, or there's some dependency between them?
In this formulation, it could be they could be non-IID as well, but eventually I'll assume their IID.
Okay, and you mentioned that you may have many anomalous nodes or random variables. So how is this integrated in your objective function? Do you want to catch at least one or all of them, or?
So this formulation is the at least one. So the error probability is the probability of X at the stopping time to not be anomalous, to be normal, right? But then if we want to generalize it to all of them, we could form a set as the outcome of the algorithm, a set of indices of the nodes, and that set of indices of the nodes not matching the exact set of the anomalous point could create the error probability term. Okay, very good question. So that is just for identifying one. What we encounter at the end, we want it to be anomalous. So the way that we could optimize this process over time or decide what action to take at every time is that we dynamically form these three cost functions, and over time we compare them. Whichever action gives us the smaller cost, that is the action that we take. So if the cost of detection is smaller than cost of observation and exploration, that is the time that we stop and we make a decision about the hypothesis. If that is not the case, then in order to decide whether we want to explore or observe, we have to see which one gives us a lower cost value. So this is a problem that generally you can solve by dynamic programming, but given the size of the network and the fact that even the horizon of the stopping time is not finite, that could become a very, very complex dynamic programming problem. So what we're interested in is finding an alternative, simpler decision rules for making these two decisions. So let's further simplify the graph that we have just for the sake of simplicity in describing the algorithms. Let's say that we have a graph network and we have the following dependency structure among the distributions of different nodes. So the distribution of node I will be F1. Condition or the probability of node I being F1 depends on the distribution of its preceding node in the graph. So it's a sort of a Markov line network. If node I minus 1 is distributed according to F0, the chance that the next sequence is F1 is epsilon 0. And if it is F1, the chance that the next sequence will be F1 is epsilon 1. Okay, so the entire algorithm or the graph will be parameterized by two parameters, epsilon 0, epsilon 1. Now, under the model, if you look at the structure of the cost functions associated with the three different actions, we'll see an interesting behavior. First, we can show that these cost functions, instead of depending on the entire data up to time t, which we denoted by calligraphic ft, they become only a function of a probability term pi t. So essentially pi t becomes a sufficient statistics for computing C1, C2, C3. And when we plot these three functions versus pi t, we'll see that they intersect at exactly 2 points. And furthermore, after looking at the intersection points, we'll see that they divide up the entire region of the cost function to three separate regions with different characteristics. In the first region, the leftmost region between for the range of pi t between 0 to pi l, we'll see that function C2 is strictly smaller than the other two functions. That means that instead of computing function C2 and C1 and C3 completely, all we need to do is to compute this parameter pi t and check whether it is within the range 0 to pi l star. If it falls within that range, without knowing the values of the functions C1, C2, C3, we can say that C2 is the dominant value, and we are going to action corresponding to that. Likewise, in the middle range, the cost associated with C1 is the smaller, and then in the third range, the cost associated with C3 is the smallest. So we somehow got rid of computing the values of these functions. All we need to do is to look at pi t and determine in what part of the range specified by pi l star, pi u star, and 1 it belongs. Okay, and then based on that, the algorithm becomes the following: that we at over time. We collect samples based on that we update pi t. As long as we are within a band, we continue taking samples. If we fall below the threshold, the lower threshold, that's the time that we discard the sequence and we start exploring and locking into a new sequence. And we continue that. And the moment that we exceed the upper threshold, that's where we stop the process and we declare the last sequence that we have been observing as an anomalous sequence. Okay. So that was a very brief overview on how we, or on the nature of the design of the decision rules. Now let's go back to the active design of experiments, which is what I wanted to focus more. So this is again the problem. The problem is that over time, we want to decide how to collect samples over time. So I mentioned that the Chernoffs principle has been around for 60 years now, and it has guided many design of such sequential experiments. And in the context of the problem that we have, this is how Chernoff's rule could be interpreted. So under each hypothesis, H0 or H1, assuming that either of them is true, we could define two different information measures. So let's say that if H0 is the true model, we define information measure D0 at time t corresponding to node I, which is the divergence from F0 to F1 of the marginal of the distribution of I conditioned on the past data that we have. So it's a conditional marginal distribution of node I at time t. Likewise, we define a similar measure when the underlying distribution is H1, and that is just found by flipping the roles of F0 and F1. And based on that, the way that Chernoff algorithm suggests working is that we identify the hypothesis that is more likely. If hypothesis H0 is more likely, or in other words, its chance is larger than half, then we select the node corresponding to which di0 of t is the maximum. So that means that for every node, we have to compute this information measure and pick the node that gives us the highest information measure. And if the other hypothesis is true, we have to select the one of t. So that m is a type, that should be d in the lower line. Okay. Now, for instance, in a Gaussian Markov random field, the way it works is the structure of the information measures is as follows. So the IT becomes a summation of a bunch of log terms, which are row ij's, depend on row ij's, which are the covariance, the elements of the covariance matrix. And we have a second term that involves ytj's, which are the data that we have collected over time. So this is how it works. And based on over time, which node is giving us the maximum measure, we will be collecting the data points over time. All right. Now, obviously, this has two main shortcomings. One shortcoming is that the decisions are decoupled over time. So if you look at the structure of the information measure, it just depends on the data in the past. It has no regards for the effect of the decision over the future actions that we will be taking, right? But on the other hand, we know that because of the dependency structure that we have in the network, every action that we take, any sample that we take, it will provide different information content for the future samples that we will be taking over time. So the impact of decisions over time is somehow decoupled, and that is what we are trying to address. So what we do is that essentially we want to quantify the information of content of the samples over time. Furthermore, we want to see each sample that we take at time, how they guide us to select the future samples over time. And ultimately, what is the overall information content that we have for a sequence of samples that we select. So to address that, we look at these two information measures. So as opposed to DIs that we had earlier, which were looking at the point-wise divergence, we look at now divergence between the samples in a sequence. So it is F1, so M1 is the divergence between F1 and F0 of two sequences S, of the sequence S, given the past data up to time t-1. And then this information measure, we normalize it by the cardinality of S that gives us the content of the information per sample that we have over the network. And in a similar way, by flipping the roles of F0 and F1, we define measures M0. So if you compare it with what we had based on the Chernoffs principle, you'll see that Chernoffs principle is just looking at the marginal divergence, whereas we're looking at the divergence between sequences of random variables. So hopefully by looking at the divergence or information content of the sequence, we could have a measure that links the different decisions over time. Now, furthermore, in order to customize it to every node, we add an index S and enforce that in order to compute that index for every node, we only look at the sequences that contain node I for sampling. So M1 will be modified to M1 I of T for sequence S. And now, instead of selecting the node, that gives us only the information based on the immediate node that we're going to select I, so just based on the marginals, we look at the node that gives us the not only the best immediate return of the information, but the node that belongs to the sequence that is the most promising sequence of sampling over time. So let's say that at time t, based on the observations collected up to time t-1, we decide that the maximum likelihood decision for the hypothesis is H0, so the first line of this sequence. So that means that we look at information measure M0. And among all the node I's, we look at the node I, which has the most or has the highest promise for the information, for having the information content for the future selection samples that we will be selecting over time. And that node, in conjunction with its corresponding sequence, is selected to be the nodes that we will be observing future in the time. Of course, all we need from this optimization is identifying the node I that gives us the best choice for time t. Once we have done that at time t+1, we have to again update the sequence S, update the node I, and continue this process. Okay. Now, of course, this has a very big challenge, and that is this optimization for selecting psi of t involves optimizing over the path S, and we have to dynamically do it every time. And the search complexity of that grows exponentially with the size of the network. So that immediately becomes prohibitive to implement. Now, one key observation that we have is that maximizing these information measures, so DIs are typos, they should be MIs. So maximizing these information measures don't have to be done over all possible sequences. Rather, what we have to do is to look at just a subset of these sequences. In other words, instead of at time t, looking at all possible sequences of the samples over the entire network, all we have to do is to search over the possible sequences of samples that are immediate neighbors of the node I in the graph that we're looking at now. Okay. So that gives us a significant reduction in the sampling process. Instead of searching over the entire space, the entire graph, we only look for the neighbors of Y, and we look at all combinations of the sampling sequences over those neighbors, and we pick the sequence that maximizes the information measured DI corresponding to that sequence. So that's a significant observation that gives us the complexity, reduction in the complexity. And the structure or the neighbors of the node I, again, are specified by the underlying probabilistic graph model that we have for the data. Now, let's just see its application on the first motivating example that it had for anomaly detection in power grid. So let's say that look at a very specific part of the grid. Let's say that we have these nodes, the buses connecting them, their corresponding power values and voltage values and phases. So phases are...
Ali, your voice is not clear. Is that just us or is there a problem?
Okay, I think here also the voice is a little bit became noisy all of a sudden.
So yes, it's noise, and the reason is that there's a funny thing happening here. There's a helicopter just next to my office landing.
There's a what?
A helicopter.
Helicopter, okay.
Yes. So
Okay.
I think, well, it was actually taking off. So I think it left. It should be
Oh.
okay now, right? So this helicopter lands only once a year here. It's an experiment for undergraduate students. So
Okay, okay.
that exactly coincided with the 1 hour that I didn't want it to happen. Anyways, so let's look at the application. So we have this part of the power grid. Let's say that the line between nodes 3 and 4 is cut off. It means that the power or the effect of that line cutoff will be sensed by not only nodes 3 and 4, but also to a different degree by their neighbors, right? And it will start propagating over the network. So what we want to do is that by observing the data that we have from this network, identify, first decide whether there is an anomaly in the network or there's a line outage in the network. And secondly, if we decide that there is a line outage, we want to also localize it, okay? So we apply this methodology. So we, based on the model that we have for the power system, we create a probabilistic model. There are significant studies that they show that power system could be effectively modeled by a probabilistic graphical model, specifically a Markov model. And corresponding to that, for all the information measures that we had, we could create the right indices. So there is one part of the index MI that captures the correlation structure. There's a second part that is driven by the data, which is the data of the phase angles. And based on that, we start collecting the data. So whatever node is giving us the highest information content at time t, that is the node or the bus that we will sample at time t. And based on that, we can see that we can localize the location of the anomalous line, the line in outage, much faster than the other state-of-the-art algorithms. So state-of-the-art algorithms before we implemented this was compressive sensing, which tries to get a compressed observation of the entire network at every time, and based on that wants to localize the structure of the network. Whereas we can show that by this active sampling of the network, we could improve. So essentially, if you look at the accuracy of localizing the index of the line in outage, and assuming that, let's say that there is only one line in outage, with compressive sensing, we could localize it with accuracy 45%. And with active sensing, we could localize it with accuracy 87%. And there is no real magic there, except that compressive sensing is sort of oblivious to the structure of the network. You have a sensing matrix which is generated randomly. It is fixed. It is not driven by the structure of the network. Whereas when we do active sensing based on the structure of the network, we can very quickly just collect samples from the parts of the network that have a stronger traces of the anomaly. So that we can lock down to where the anomalous event has happened with fewer samples. And if you look at the outage events of larger scales, when we have 2 lines in outage or 3 lines in outage, the same improvement, the same trend of improvement holds as well. All right. So just also looking at the computational complexity due to searching for the best sampling sequence that we have. So we are looking at 3 or 4 examples in the 118 bus model when we collect 30 samples or 50 samples or 70 or 90. And in each of them, we look at the time required for collecting or solving the problems. So the last row is exhaustive search. The second row is the exhaustive search. That is the time that a regular machine in our lab requires for solving the problem. And then the first row is based on dynamic selection of the actions over time, dynamic sampling. And then we look at the ratio in the third row, and we'll see that when we have only 30 samples, or we can afford to collect 30 samples, exhaustive search will be taking 23 times more number of samples, or 23 times more time, computational time, for finding the best action, which is the sampling decision over time. And the same trend continues as we collect more samples. All right. So that table reflects on the sample complexity for searching this optimization problem. which was the key observation, that on the left side, we do an exhaustive search over all possible sequences for identifying the best node to sample. On the right side, we had this conclusion that, look, we don't have to do an exhaustive search. All we have to do is to look at the neighbors of the node that we have observed at time t-1. And based on that, select only the best node from that subset of the nodes. So these two rows of the table essentially show the computational time that we need for solving the left side and the right side of this equation. All right. So let me stop there. I guess, yeah. So now, if there's any part that you'd like me to go over or you have any questions, I'll be happy to answer.
I don't think there's a question on my side, at least. So do you still have part that you want to cover, Ali, or you're done with the slides?
I'm done.
Oh, okay, okay.
Yeah.
So you mentioned at the beginning you may want to talk about like kind of fundamental bounds, maybe, or I missed it.
Let me see. You mean performance bounds?
Yeah, performance bound, yeah.
So I don't have the performance bounds in the slide. Generally, so the nature of the bounds that we provide is how the sampling size scales over time, right? So here. So generally we look at, some people call it the average delay, some call it the sample complexity. But generally the nature of the results, the average number of samples generally have this form. They're related to different information measures. So I guess it very much depends on the structure that we have for the network, depending on the distributions. But all of them, in essence, they boil down to divergence terms. So specifically KL divergence values, similar to this case. Now, of course, there I0 and I1 will be the divergence between sequences of distributions, not just marginals. But that is the nature of the guarantees, performance guarantees.
And another question from my side. So would it make sense, especially in the application you mentioned, you could have maybe sense of measuring linear combinations of the data, and then like something in between the compressed sensing,
yes.
what you're doing, like
yes.
active.
Yeah, that's a very good point. Yes, functional sampling. Let's say that instead of looking at sample X1 and X2 separately, look at the function of X1 and X2. It could be a linear combination like what compressive sensing does. We could be doing it more intelligently by selecting the sampling weights, or it could be any other nonlinear function as well.
Yeah, I mean, wouldn't, like in the power example you gave, wouldn't maybe measuring a current, which is like at a certain point it's going to be the sum of things, or you kind of get it for free? I'm not sure what's the data in there is, but
so there usually the data is power, is voltage, and phase angle.
Okay.
So yes, and it depends what parameter we want to look at, right? If you want to look at the currents, of course, we can, based on those three values, you can also infer what the currents are, and then look at the anomalous behavior of the currents.
But also the voltage, right? I can choose the voltage between which 2 points, and this will give me maybe some function of the individual voltages that I get.
That's right. So that's essentially what is very helpful, right? So let's say that you make a decision about the voltage of any point in the graph. Because of the interconnectivity of the nodes, the voltages cannot change freely, right? The voltage.
Yeah, exactly.
Voltage, if you fix, let's say that you have a triangle, if you fix the voltage of 1 and 2, the third voltage will be always dictated by those two voltages. So just sampling 1 and 2 could be enough also for deciding what voltage 3 is, right? And that is what giving us this network structure. And that is essentially what we are leveraging here.
Okay. Okay, so I don't know if, I think so. Yeah, you can go ahead and ask question, whoever.
Hi.
Hi.
I had So you described some classical theory in the beginning, dating back to Chernoff with these design of experiments and so on.
Yes.
I was wondering for the application to the networks that you're talking about later, to what extent is that kind of an application that fits completely within the classical theory, and to what extent do you need to kind of like extend the theory in order to handle this network scenario?
So there was one counter example that I think I skipped over. Let me go back to that. So whenever we face sampling, so sampling, you could think of it as the design of experiment, right? What node to sample at time one means that what type of experiment I want to run to take that sample, right? So whenever we have dependency of the decisions over time, and by that I mean statistical dependency, generally the Chernoffs principle does not work. This is a very simple example. So let's say that we have a graph of n nodes, and it consists of two independent subgraphs. So the first, each of these two subgraphs is a linear graph, and we have a Markov dependency structure there, which means that x2 depends on x1, and there are Gaussian Markov with covariance value or correlation value larger than a, and x3 depending on condition on x2 becomes independent of x1 with correlation factor again between x2 and x3a and up to xr. And likewise in the other subgraph, we have correlation coefficients that are smaller than b. So if you look at these graph, and let's say that our test is to decide whether all these n random variables are independent or they're generated according to this Gaussian Markov random field. If we do that by our analysis, we can show that the ratio of the average number of samples that Chernoff requires compared to the optimal approach of selecting the nodes will be A over B squared, where A is a value larger than B. So you immediately see that Chernoff is not optimal anymore. Chernoff's principle is not optimal anymore, even for this very simple network structure. As you make the network structure stronger, that deviation from optimality becomes even more significant. So essentially for addressing these, there is the need for new theory. And that was the core part of it, which I mentioned, is essentially coming with a way that you could link on a very principled way all the decisions that you make over time, how you can connect the decision at time one to the decision at time two to the decision at time three, and so forth. And for that, we suggested this information measure that links the decision over time, and we can show that this actually achieves the optimal performance. And that is usually done in two elements. First, we establish a converse, that what is the minimum number of samples that any algorithm requires. So we establish that bound, and then we show that this approach that you're suggesting achieves that bound, which means that the sample complexity of this approach is exactly that lower bound that we have seen in the converse. Did that answer the question?
Yeah, thank you.
Okay, so if there's no more questions, I want to thank Ali again for the nice talk, and thank everyone who joined us. And we'll see you again next time. Thank you, Ali.
All right. Thank you very much, Sally.